Hello, everyone. Thanks for coming to my talk. Thanks to the Memoization guys for organizing this great conference and bringing me here. And first, I would like to tell you a bit about myself. I'm a software developer, have been programming professionally since 2001. And I found Lisp in 2005 via programs, essays, and books, for which I'm forever grateful to him. And I found Clojure on Hacker News in 2010, fell in love, haven't looked back since. Since 2018, I'm an independent contractor for Cognitect. And if you'd like to learn more about me, you can visit my website at biserkov.com. Also, in my free time, I'm a wildlife survey drone pilot, as you can see from the photo. But most importantly, I'm a gamer. And I'm a gamer who plays games for the story. Not for the graphics, not for the action, for the story. And I've noticed that no matter what kind of a game, if it's a first-person shooter, if it's an RPG, if it's a strategy game, if it's a racing game, they all have the same story. And in the beginning, there's this huge challenge, this big problem, which is incomprehensible, which is impossible, some might say. And on the other hand, you have the main character, who is so small that you can't even call him a hero. He has a crappy sword, or just a single pistol, or the slowest car in the world, but he has a vision for a better world. And so he starts small, completing some challenges, leveling up, learning new tricks and skills, maybe doing some side quests, meeting some allies, defeating boss after boss until he confronts the final boss and wins happy end. Everyone's happy. So you're wondering what this has to do with graph theory, with trees. So it turns out there's a lot of similarities between the journey a computer character takes and I took while implementing this novel algorithm for my master thesis. So I invite you now to come with me on an epic journey in the two trees forests, where the end goal is to implement the big ON boss. But first, we need to go into the bottom levels, where we encounter some OK bosses. And we will see the first use of my superpower. Then we'll get to the next boss, complete a side quest, seek the ancient structural tree, then encounter the next boss. Then suddenly a wild Stack Overflow appears, and I don't mean the website. And then there's the final fight. So you're probably wondering now, what are those two trees? So before I tell you what they are, I'll tell you what they are not. So two trees are not binary trees, and they're not even trees. Instead, two trees are a class of undirected graphs. They're used to model electronic circuits, and they're recursively structured. The simplest one is just two vertices connected with a line called an edge. And then you recursively, when you add a new vertex, you connect it with exactly two edges to exactly two vertices, which are already connected with an edge. So what you end up with each new vertex, you add a new triangle, a new face, so-called, to the two tree. And now some background about the algorithm and the task at hand. So since the 90s, there was an algorithm to compute the length of the longest path in a two tree in linear time, but it has colossal hidden constants, so it's linear in pretty abstract sense. It has never been implemented. And in 2013, three Bulgarian professors, Markov, Vasilev, and Manev, published a novel algorithm, which they implemented as pseudocode in their paper. And so our main goal is to implement the MVM algorithm in ON time. Just a quick overview of the algorithm. It recursively splits the two tree into subtrees. And in doing so, only a few nodes change. So it's a perfect fit for Clojure's persistent data structure. That's why I decided to use Clojure in the first place. And it keeps doing that until it reaches the leaf edges, which is the boundary condition for the recursion. And they get a label of 11000. And then going back up, it combines the labels of the subtrees to compute the parent tree label. And then the first element is the result that we need, the length of the longest path. So each of these labels, they basically store all the state that you need from this subtree that you can, once you have the label, you can forget about this subtree and continue back up. And on the code structure, there are three levels. There's this top level compute label function, which is the recursive one, and does the splitting. On the middle level, the two functions for combining, depending on how the tree was split, either on a face or an edge. And on the bottom level, just two very simple or simple seeming helper functions. So let's start with at the bottom. I couldn't implement the top before implementing the bottom. So A and B are just two vectors with k elements. And you need to implement this simple-sounding mathematic one-liner, which says that take the maximum sum of two elements from each array or vector, but only when their indices are different. And so that's quite easy to code in Clojure. But we hit a problem. Because we have two nested for loops, this has OK squared runtime. And why is that? Because you have to basically walk a square of all the combinations of those two vectors. And for the algorithm to be linear time, you can't do that. You have to implement this in OK time. And so the way to do this is to iterate each vector separately, keep track of the maximum, the second maximum, and the index of the maximum. And then compare the two indices. If they are different, you can just use the two maximums and you're done. But if they're the same, you have to make the other combinations. The largest one from A and the second largest from B, or the largest from B and the second largest from A, and choose which is the bigger one. And so we defeated this boss quite easily. But then we go to 3 dimensions. And in the paper, this is left as an exercise to the reader. And so can anyone guess? Yeah, it has an OK 3 cube runtime because you have to walk the entire cube. And so once again, the way to do it faster is to iterate each vector separately, keeping track of 1, 2, 3 maximums and 1, 2 indexes, and then check which of the 36 combos are actually valid and which sum is the largest. And this leads to terrible complexity and many, many bugs. And so this is the first time our hero discovers their superpower, which is generative testing, also called property-based testing. And it's very good because it finds complex bugs immediately, but it's usually difficult to come up with a useful property of the algorithm that you need to test. And so what I discovered is that I can use the naive implementation, which is a single for loop that's basically provably correct. I'm totally certain that it does what it needs to do, and use it as equality to the faster implementation that I'm currently writing, which has still bugs in it. And it not only does it find bugs, it also shrinks the input to the minimal case. So you can see a small vector with ones and zeros in it and not some huge thing. And so we've defeated the first few bosses. And now let's look at what other heroes have done trying to slay this boss and see what they've done. So the previous implementation of the algorithm that existed, which is published in a scientific journal, is in Java. And the 2 tree is represented as a matrix. And the sup tree is a sup matrix, and so there are tons of copying. And so it's ON squared runtime for an ON algorithm. It's terrible, but that's not the worst of it. The worst of it is there's ON memory usage. So like a typical Java program, it runs out of memory before it gets too slow. And so for my first implementation, I chose Clojure. And I implement it as close to the paper as possible, word for word. And the 2 tree was represented as a map from int to a set of int. And you might be asking, why a set, why not a vector, why not a list? It turns out that for the purposes of the algorithm, the order really doesn't matter. So a set is OK. And at the same time, there can be no duplicates in this data structure, so a set is even better. And there are also several set operations like union, intersection, and difference that are used quite a lot in the bottom levels. So using set is great. But then I measured the runtime, and it was ON square root of n. And I'm like, perhaps Clojure's dynamic typing is a problem. So I decided to optimize it by using Zach Tellman's int map and int set, which are specialized versions optimized for integer keys or integer elements. They're based on the Patricia trees, quite interesting data structure in itself. And so you see here, for example, the 0 vertex is connected to all the others, so its neighbors are 1, 2, 3, 4, or the 1 vertex is connected to 0 and 2, so we have 0 and 2 here. And that's basically it. Runtime is faster, but complexity is still ON square root of n. Wow. Why? I don't know. And then suddenly a side quest appears. And the side quest is to find 5 bugs in the third-party library. The problem manifests itself as a null pointer exception. I'm writing Clojure. Why? And Recursive Debugger came to the rescue because it has this really awesome feature where you can set a breakpoint on exception and really see that You're not doing anything crazy. The problem is in the third-party library, in third-party code. And so Zach Tellman is a great guy and fixed the bug quickly. Problem has evolved. Now it's an infinite loop in a subgraph walk doing the multiple recursion. And I'm like, how? Why? Turns out that an element was added to the set twice, and then the difference operation removed only one of it, and so the second one remained, and it broke the boundary condition of the loop. So Zach fixed this bug as well, and for 5 times in a row, I would download a new version, run my implementation, and you'd find a new bug. And at some point, I'm sure Zach was thinking that I was just messing with him, but that's just the way it was. And it's very interesting that all of these bugs were introduced during a rewrite of the library from Clojure to Java. And none of those bugs were caught during extensive generative testing via the collection test library, which he developed specifically for this purpose. So nothing beats real usage. So going back to the algorithm, what was the root cause of the slowdown? And it turns out this was the splitting into subtrees. And persistent data structures are not the problem. They are fast enough computing which vertices need updating. That's the actual thing where the program spends its time. And so I talked to the authors and told them, well, this cannot be implemented in linear time. And they said, well, of course not. Why would you do it this way? Well, as if it's not described in this way in the paper. And they told me to seek the ancient structural tree. And so if you remember the 2 tree from the previous slides, so the green ones are the original 2 tree, and the blue and yellow dots are the members of the structural tree. And so the blue nodes are so-called face nodes because they sit in the middle of a triangle. And the yellow ones are edge nodes because they sit on an edge. And the red one is the root node, which is an edge node, which is the first one. And face nodes can have exactly 2 children, while edge nodes can have 1 or 2 or many. And I was looking at this, and how would I implement this in Clojure? I mean, if this was C or C++, I would just maybe do some pointers and stuff, but how would I do this in Clojure? So I kept looking and looking, and then I realized that the blue nodes can be represented implicitly via the parent edge and their third vertex in the face. And so the representation I used is a map from edge to vertex, to a vector of vertices. So for example, so for example, this blue node here is represented by this parent edge, 0, 1, and the third vertex, the 2. And here, for example, this face here, A, is represented by this parent edge 0, 2, and then 3, which is the third vertex. Also notice that external edge nodes are represented implicitly as nil because there is no new information. There is no need to put blue nodes here as it was in the original implementation. And so this led to my second implementation, which has a iterative pre-processing step, which builds the structural tree, and then the recursive parts operates on the structural tree and not on the 2 tree. I measured the runtime has improved, O(n) log n, but still it's a lot more complex, unexplored territory. Once again, generative testing saves the day. Found several bugs I would never find otherwise by using the old implementation as a test whether the new implementation is correct. So you get the best of both, straightforward and correct, but slow, and the other one, which is complex and unproven, but it's faster. And then suddenly, a wild Stack Overflow appears. And I'm like, why? Infinite recursion again? Another bug? No, all tests pass. Then what is happening? Turns out this is a genuine Stack Overflow because one of the benchmarks was using a special case of ultra tall 2 tree. Like, imagine a normal tree. If you don't balance it, it degenerates into a linked list. The same thing can happen in 2 trees, so I had made this special generator to generate ultra tall 2 trees, and this would overflow the stack. So I Googled around, and the first workaround that I came up with is just increase the call stack. Via the JVM options. JVM is very flexible, but after I double the n, which is the number of vertices, a few times, the problem reappears. And so I thought, well, I've studied computer science back in university, and every recursive algorithm can be made iterative by using an explicit stack as the parameter and not use the call stack. And just as I was looking for stacks in Clojure, I realized that I already have a data structure in my program which holds all the information that the iteration needs to resume. And this is the edge vertices map that we saw previously, representing the structural tree. And with some modifications, the recursive calls can be removed completely, and all the work can be done during the pre-processing bottom-up phase, going from the leaves to the root, completely eliminating the recursion going from the root to the leaves. And so my third implementation is an iterative one. It's based on dynamic programming, has no recursive part, has ON runtime, finally, and can compute the longest path in 2 trees with millions of vertices without overflow. And the map that we had from edge to vertices is now a map from edge to vector of labels. And generative testing saved the day yet again, found even more bugs. And so this is the end result. We start with 100,000 vertices, and we end with 6 million. And the red line is the projected ON log n time, which is bad. And then the orange line is the projected ON time. And the actual time is even faster. But as you can see, we've doubled the input size 64 times, and the runtime has stayed consistently linear with the input size. And so, all the benchmarks were done with the excellent criterion library by Hugo Duncan. It was very good because it's much more accurate than just using time, because it pre-warms the JIT, does a few cycles before it stabilizes, and then measures the actual runtime of the hot program. And it also outputs statistics which show you the standard deviation and the percentiles and stuff like that. Shows you if there are outliers, how much time was spent garbage collecting and stuff. And so, quick implementation recap. We started with a Java matrix ON squared runtime. Then we implemented in Clojure the recursive one, which is based on int map and int set. And it's better, but because of the subgraph walks, we still have this square root of n. Then we switched to the structural tree one, which is still based on int map and int set, but then uses the vertices map. And it's n log n because it builds the entire tree, and the tree can get pretty big. And then the final implementation is bottom up only. It uses the int map and int set data structure and also the edge labels. And it's ON because it does not have to build the whole tree. It starts from the bottom, and it can discard the levels which are already processed. And so we've defeated the final boss. What is left to do? Let's replay the game and find some more optimizations. So one thing you can use is transient variants of persistent data structures, because sometimes it's really OK to mutate the object in place. If after the operation completes, it's no longer used, nobody's referring to it, you can just mutate it in place and still maintain an immutable interface to the outside world. But this adds a bit of complexity, so my advice is to first make your program work without it, and then it's very easy to convert it to a transient one. In the beginning of the loop where you initialize the data structure, you just add a call to transient around the constructor, and then you add a bang to each assoc, disorch, or conjure, or the similar operations, which are the versions which operate on transients. And then once you're done, you call persistent to get a persistent data structure back. And I'm not sure at which point I implemented this optimization, but it reduced the running time by 10 to 20%, and also decreased memory usage quite significantly. Also, once we've optimized the high-level function, now we have more knowledge inside it, and it turns out that we can optimize the middle-level function. So the proper case, which is 2 tree with 2 non-trivial trees, is greatly simplified and a lot of branching is removed. The degenerate case where one of the branches is a trivial tree is also greatly simplified, removes branching, and a lot of operations become faster because when you know that A is 1, A plus B becomes simply inc B. Or when you know that C is 0, max C and D simply becomes D. So this, and the trivial case where both of the edges are trivial is handled by the higher level function. There is no function call, there is no necessary computation. And that's one example of, as I like to call it, unrolling recursion. Because when the mathematicians came up with the algorithm, they wanted to be as general as possible, work in all cases. But when you're implementing it, you want to lift up the base condition wherever possible to avoid all kinds of recomputations and be able to make decisions at the higher level saves a lot of time at the lower levels. Another trick I come up, not come up with, I used in this whole thing, and that's, I believe, the reason why the algorithm was able to be faster than the projected one, is that I used memoization. And what this means is a function remembers the result it computed for a given set of parameters. And so the next time it receives the same parameters, it just looks up in a map and returns the result without recomputing the whole thing. And so this is very useful whenever a big problem is divided into smaller ones, because many smaller ones can be identical, and you can just reuse the computation that you've performed without any significant cost. So Clojure has a built-in memoize function, which works great, but it returns a variable argument function, which adds some overhead. And in this case, we knew exactly the number of arguments, so I just created a version which uses this one, and this is faster. And so resources, you can learn about the algorithm itself on this website. You can find my implementations on my GitHub. And you can learn more about Clojure transients at this awesome website by Jean-Nicolas Dorange, if I'm pronouncing his name correctly. And that's it. Thank you for coming with this journey with me.
OK, now that Panu is gone, Joel is trying to fill in.
Thank you. You said you are wondering about how to represent the structural tree. Was there a reason not to just use a linked structure for it? I mean, because that's the obvious, persistent way to represent the tree, right?
How do you mean?
Well, you have like, basically, if you think about how to represent like a binary tree in Clojure, you have a map with left and right keyword, and then those point to the left and right subtree. Yeah. So like a simple linked structure, recursive structure.
I see what you mean, yeah. That could work, but would be a lot more tedious to implement, and it turns out it's unnecessary for the algorithm.
No. OK. Yep.
Yeah.
Any more? Go ahead, Joni.
You mentioned an application in maybe printed circuit board traces.
Yeah.
Can you elaborate a bit on that? It went by pretty fast.
Yeah. So basically, the two trees are the maximal series parallel graphs. And so the series parallel graphs are used to model series or parallel electric circuits. And so two trees are a superset of them and can be used for those purposes. And there also, two trees are a special case of K-trees, which are another class of graphs where the one trees are the normal trees. The two trees we saw are made from triangles. The three trees are made from pyramids and higher dimensions as well.